why we're here. We are in the everything digital era. This is a beautiful chart that was produced by Bell Laboratories I came across just recently, and it divides the internet era into several epochs. And the most recent one is the one that we're in right now, where everything goes digital. And this started 30 years ago with what we call the pre-internet era and the browser era. And in between that was the telecommunications era, when telecommunications and telephone calls went from analog to digital. It was really the first. Now, today, of course, everything, because we've gone through the desktop digital era, the mobile era, to the point where each of us is walking around with a supercomputer in our pocket, consuming digital media, streaming videos to our phone, watching movies, partaking of the world's knowledge, social networks, you name it, on our phones. But that's just one example. Today, I have a slide, a couple more slides into this, where I talk about just the wealth of applications that we're all taking for granted now. And it's all driving the demand for bandwidth, which is what this curve is here. This represents the integration of each of these epochs that Bell Labs determined. So, along with those succession of epochs, we've seen this continuous downdrop, this continuous scaling of interconnects to shorter and shorter form factors. It started, as I said, with telecommunications, where satellite links were replaced with transoceanic and transcontinental links. It started off as copper, and then as demand increased and as latencies and capacity needed to improve, it increasingly went to optical fibers, again, starting about 30 years ago. But then the links became shorter and shorter. We started to see regional and metropolitan links, fiber to the home, and things of that sort. And then the data era, that epoch that started with browsers and search and continued on to the desktop, that started happening. And you ended up having companies like Google and Amazon and Apple and others building immense data centers because of the world's appetite for data. And that's only increased as time has gone on. So the links just keep getting shorter and shorter. And soon it will be, right now it's to the point where we're seeing it, the demand in the data centers for rack to rack and box to box, but soon it will be card to card, chip to chip, and then the cores and other structures in the chips themselves to get data from memory and data storage into processors for correlation and processing. This will increasingly be done using photonics for a variety of reasons. Here's one thing I don't think is going to happen again. Back in the last photonics boom years, starting around 2002, the bottom dropped out of the market. And the photonics industry just ceased. It stopped. It didn't have a pulse. That isn't going to happen again, because back then it was all about telecommunications, a single application. Today, it's about more applications than you can point at. You have big data, you have Internet of Things, which is sensors everywhere, including in industrial equipment. That's Industry 4.0, with everything connected to everything else so that predictive maintenance can be performed and processes can be monitored to the nth degree. Everything can be measured. Smart cars, smart cities, and this is one of my favorite charts right here. This is the impact of genomics on medicine. A friend of mine is in his late 50s, he's never smoked in his life, developed a cough. He went to his doctor. His doctor said, well, let's do an x-ray. He came back and said, are you sure you never smoked? Because he had a tumor, a lung tumor, the size of a grapefruit in his chest. It had just developed in the space of 3-4 weeks. So they did a needle biopsy, and they did a genomic scan of the tumor that he had, and they determined the precise genetic mutation that his tumor had. And then they did a correlation against thousands of other people who had had similar tumors to determine what the best course of action was. It turned out a recently developed drug would target that specific mutation. But think about it. Terabytes of data had to flow back and forth for the correlation to occur. And that's what you're seeing right here. And this is one of the applications that is driving the consumption of data. Happy news, he's responding very well to this particular chemotherapy. No side effects. And within the space of 2 weeks, the tumor has gone from the size of a grapefruit to the size of your little finger. It may just be scar tissue now. So they're watching it. 6 months later, he's fine. If this technology had not been in existence, he wouldn't be with us anymore. So this is all causing data to be consumed at an exponentiating rate. This is a log plot, base 10. It shows the consumption of data over a period of time. So you can see this isn't going away anytime soon. It's not like 2002, where the amount of optical fiber that long-haul telecommunications needed saturated. There was enough dark fiber laid that they just didn't need anymore for a few more years. So the bottom fell out of the market. That isn't going to happen anymore because we have so many applications driving this. Something else, and that is energy consumption. It's much more efficient to convey bits of information using optical techniques, photons, than it is to do so by charging, discharging a wire, especially a long wire. But even short ones, even in a conventional computer, the study has been done that in your computer itself, or in your telephone, your iPad, about half the energy, actually more than half the energy, consumed by that device is consumed in moving data around inside the device. So this trend is going to continue as well. And again, smaller and smaller scales. So it's important. What we're seeing is that photonics is the future of computing and the future of semiconductors. What has to stop, what has to not happen ever again, is for the industry to be unprofitable. This is one of the reasons that photonics died in 2002. And it's up to us, the people in this room and the people we work with, to prevent this from happening again, to provide cost-effective technologies that not only address the technical issues, but do so in a sustainable economic way. So that's why this is such an important sort of event for us and for our industry, because it's all about the networking. It's all about the community of participants that sharing what they can share. I don't ask any of you to divulge anything to anyone else that is proprietary, but I guarantee you that everyone in this room is seeing the same problems. Every one of our customers is seeing the same problems. They need solutions that are economic and fast and do what they need to do and keep pace with the increasingly tight tolerances and increasingly numerous interconnects that today's devices are presenting. So everyone faces the same issues. It's important that we share problems that we're facing, that our customers are facing and our partners are facing, and also the solutions, because everybody benefits when those solutions scale, when they're adopted broadly. So please, over the next day and a half, please brainstorm, partner, collaborate, and share. That's one thing that EPIC does a fantastic job of doing. And much credit to EPIC for fostering this community of collaboration. Okay, I've been asked to give a little summary of what PI does. Well, most of you know us. We are a motion control manufacturer. We are the leading manufacturer in the sub-micron world. We are a global company with sales, service, support, applications, engineering all over the world. We have special expertise in photonics. We have collectively over 100 man-years of photonics experience, photonics alignment experience. Rhonda Gauss is one of the pioneers in the industry. Gabriella is one of the people who's really helped our customers over a long period of time in developing more and more sophisticated approaches to integrating precision motion to achieve rapid alignment. Of course, I've had some exposure to that myself. So we have some special capabilities that have started in the nanoscale world, where we are primarily known for our piezoelectric nanopositioning, where we make our own piezoceramics to give us performance and reliability capabilities that no one else has. And then from that foundation, we've moved to larger and larger motion form factors, to the point where today we have large gantries, air bearings, things of that sort. Basically what this means is we have a very, very broad toolkit, including very novel piezo mechanisms that provide long travels together with extraordinarily high resolution, very compact. This is a device that's about the size of a matchbook, and it provides resolutions in the nanoscale and travel ranges over tens of millimeters. Really very remarkable capabilities. Then, of course, the big linear motor stages, things of that sort. One of the most recent additions to the PI family is ACS. It's a manufacturer, very world-leading manufacturer of industrial motor controls. So that allows us to safely and quickly move large structures like the stage you see here, and do so in a way that may integrate other types of motion devices, so that you could have many centimeters of travel together with its nanoscale alignment automation, and lots of capabilities and lots of unique features, such as vibration cancellation that eliminates settling times. And it all has to do with speed and throughput, speed and throughput, speed, speed, speed. This is what customers need to become economically viable. Alignment is a severe case of that. Here are a couple of slides that are pretty interesting, I think. This is from IBM, where they're talking about the comparative cost of packaging for photonic devices versus conventional microelectronics. The orange represents packaging costs, and that's dominated by alignment. You can see right here, they say packaging is key to the lower cost of photonics. And yes, that's very much the case. Here is a chart. It dates back about 10 or 12 years from Journal of Lightwave Technologies. And here, the authors looked into the contributors to device costs. And you'll notice alignment has the largest of these bars right here. The interesting thing is that alignment is also a part of all of these. So if you add up the embedded alignments, the alignments that are kind of hidden in the processes, this gets even taller. So alignment's really important, and what this adds up to is the problem statement, where you find that alignment is the dominant cause, the dominant cost for photonic device manufacturing. I'd like to say a word about one of the unicorns of the industry. For the past 30 years, people have been saying, well, what about passive alignment? Maybe we can do passive alignment, design our devices, and manufacture them to such a fine degree that we don't need to do any alignment automation. The alignment would be automatic. Pieces would just fit together like Legos. Well, maybe. There has been some work on certain types of interconnects that looks very promising for those particular limited use cases. I do not see these technologies being propagated across the full spectrum of alignment, far from it. I see it being an option for a certain class within a certain subclass of device types and manufacturers and people who pay the license fees for these technologies. I do not see it becoming a general purpose panacea for device manufacturing economics. But I just don't see that happening for several reasons. There are, for example, many interconnects that instead of being a linear array of fibers spaced at 127 or 250 micron intervals, which is what the IBM study that these graphs are from discusses. Instead, we're seeing rectilinear arrays and polygonal arrays and some very novel arrays I'll show you in a minute that reduce the core-to-core distance from 10 to 40 microns. So instead of being 250 microns apart or 127 microns apart, it's a tiny fraction of that. And so the tolerances, the device manufacturing tolerances have to scale accordingly. And frankly, we've, here at PI, we've developed alignment technologies that are so fast that it really isn't worth the effort anymore to pursue the passive alignment approaches. So I don't see that becoming very much a factor in the general manufacturing of these devices. I just don't. There's our problem statement. Alignment is the most highly leveraged cost in photonics manufacturing. Alignment has been lengthy, time-consuming, expensive, with poor yield, and needs to be repeated multiple times during the test and packaging of photonic devices. So all of those costs get multiplied by the number of times that you need to perform this, starting at the wafer level and continuing on through final packaging. Today, the alignment challenges involve multiple degrees of freedom. You have multiple inputs. Today's devices are almost exclusively array devices. We are seeing very few new applications that involve a fiber connected to a laser, the way things were 15 years ago. Instead, it's arrays, devices on a chip, and multiple inputs, multiple outputs. Anytime you have an array device, you have theta Z, and anytime, irregardless of what kind of array it is, whether it's a linear array of fibers or something like what I was mentioning just a few minutes ago, the PROFA arrays from Karlsruhe Photonics that have a pitch of 10 to 40 microns between channels. So you always have theta Z involved, and you may have other degrees of freedoms as well, in addition to the transverse and potentially the Z alignment, depending on the device. So worse than that, these degrees of freedom interact in that when you move in an angle, you also need to go back and recorrect in X and Y because your pivot point is probably not exactly on the optical axis. So that means you need to do these lengthy, repetitive loops of transverse alignment followed by an angular motion and then another transverse alignment to correct the damage caused by the angular motion and things of that sort. Plus, the channels themselves, inputs and outputs, can steer each other for these devices, for the short waveguides that people are using. So you have these input and output steerings, you have geometric parasitic de-alignments, and it just gets more and more complex, and you have more and more channels, tighter and tighter pitches. So, one answer, we think, is the use of hexapods for alignment. The benefit of a hexapod is that you can cast the rotational center point anywhere in space. A hexapod gives you 6 degrees of freedom, and it allows you to rotate in a Cartesian coordinate system that you can, with the software command, place anywhere in space. And this is a very powerful capability because that means you can put it at a focal point or a beam waist or an optical axis for doing the angular alignments. That allows you to minimize, but chances are not completely eliminate, these parasitic motions. So that's a very beneficial capability. One thing I should point out, usually in my presentations, I like to spotlight our customers who are building our technologies into their tools that they in turn sell to the end customers. I'm not doing that today because they're here. This particular video right here is courtesy of Form Factor, and it shows you the ability of the hexapod to rotate about a fiber tip at the end of a fixture. Very, very powerful capability, very helpful for these applications. Putting it all together, when we combine hexapods and the large motions and the piezoelectric motions, that's what we do. Building subsystems that allow our OEMs to build tools and solutions for their customers. Built into our controllers are 2 basic categories of alignment technique. The first is an area scan. It's a brute force approach where you take one device and you scan it across the other in whatever degrees of freedom you care about. Conventionally, this is a raster scan or a serpentine scan, but that's not what we do with our current firmware. Instead, we have a sinusoidal scan and a spiral scan. Constant frequencies. You choose the frequency. The benefit is it's a smooth motion. It doesn't stop and start. And because you can choose the frequency, you can avoid the structural resonances that might occur with the conventional scan. So it's faster. And again, speed and throughput. That's what the end customers need in order to achieve economic viability for what they're doing. So this is a very powerful approach for finding the approximate location of the peak. But today's devices, we're seeing localization tolerances down 20 nanometers or less. And in order to do that with a conventional or with an area scan, you need to have these scan lines that close together, and that would take time. There's another drawback as well, in that today's short waveguides and the geometrical parasitism that I mentioned earlier, this can't compensate for that in real time. What can is gradient search. Gradient search is a classical technique. It's been around for a while. It's been through several advancements, including one that I'll be talking about in just a moment. What gradient search does is you move one device with respect to the other in whatever degrees of freedom you need to optimize, and you perform a small circular pattern. So again, it's a single frequency, so you can choose that frequency so you're not causing any mechanical issues in your structure. And what that does is a diagram. If you take a look at the mountain, and here's your circular dither. When you're at this point in the device's travel, you have this much power. When you're at this point in the dither, you have this much. So as you move around the dither, you vary the coupling, the throughput, optical power that's going through the system in this quasi-sinusoidal way. From observing the phase and amplitude of this modulation, we can determine which way is up. The benefit of this is that it can track. So that if this moves, we see the phase start to manifest itself, and that tells us we need to move along with it. So we can do tracking. We can track drift, we can track curing stresses and things of that sort. And what we've done that's very unique and very new is we've implemented this in a way where you can do this in multiple degrees of freedom, multiple outputs, multiple inputs, multiple channels, all at the same time. So that means, for example, that going back to the example of an array, where you have transverse alignment and also a theta z alignment at a minimum, we can do all that at once instead of doing it sequentially, which takes a lot of time. The benefit is it's about 100 times faster. I'll show you. Parallelism is the difference between this and this. Not only are the individual processes faster, but you can do more of them at one time. Example, the array alignment, where you have a pattern of channels, either fibers all in a row or in some sort of rectangle or some sort of polygon or one of those PROFA arrays from Karlsruhe Photonics. Basically, regardless, if you have more than one channel, more than one fiber, you have this situation where you can align one channel in XY, but now you have to do theta z as well. And because your rotational center point is probably never going to be exactly on the optical axis, even if you're using a hexapod, then any motion in theta z will cause a de-alignment in XY. So you have to go back and fix that and do the XY alignment and fix the XY alignment, and then you can make another theta z motion, and you do this all in a loop until everything is aligned. And this can take a couple of minutes, or you can do it all at once with parallelism. If you can do the alignments in XY at the same time as you do theta z, and other degrees of freedom as well. Do it all in parallel, do it all in one step on both sides of a device. And we're even seeing devices with more than two sides now. So we can do all those alignments in one step instead of this lengthy loop that takes a long time to do. And so that is about a factor of 100 faster than it would be to do things sequentially the old-fashioned way, and that's 99% cost savings in that tall bar in the bar graph. Here's an example. From Photonics West in 2017, January 2017, we had this demonstration using 2 fiber arrays, which are an accurate simulation of what our customers want to do. So what we did is I built a little application using our software tools to perform with rapid scans to localize the peak, then a gradient search to lock onto it with a theta z gradient search in parallel, and we're done. So this got a lot of attention, as you can imagine. It's not something people have seen before. This year, we had a double-sided array, array input, array output. And again, built an application that would do the same thing on both sides with the lock-on on both sides at the same time, and theta z on both sides, and we're done. So here we're doing one of the most difficult chores in photonics, and we're doing it quickly, and we're making it look easy, because with these tools, it is easy. I mentioned that it's getting a lot of attention. What better way than to show you some scenes from some recent trade shows. There's OFC conference, and there's the Clio conference, left and right, respectively. And you can see people who are walking past this, and they have trouble believing the system can do what it can do. Because this is a process that anyone who's worked with array devices in grad school or in industry knows is extremely difficult and very time-consuming to do. And here we are doing thousands of these alignments during the course of a conference. Okay, another example, wafer probing example. Here you have devices that have an input and an output, and because the waveguides are very short, they tend to steer each other. So you align the input, and then you align the output, but that changes the optimal position of the input, so you have to go back and do that again, and then that changes the optimal position of the output. So again, you have this loop that takes a long time to do. Instead, you can do it in parallel. Do the alignments on the input and the output in X and Y. If there are thetas, do them at the same time. Do theta Z, do theta XY, do the Z for determining a focus if it's a lensed coupling. Do it all at once. And again, enjoy that 99% reduction in cost. Here we go. We're going to do the input and the output of a wafer. We just did that. We did the input and the output at the same time. It took about 300 milliseconds. Here it goes. So speed, speed, speed. When you have a wafer filled with thousands of devices, and you need to test those devices because, as you've seen, the cost is in the packaging. You don't want to package bad product. You're just burning money when you do that. So they need to be tested at the wafer level, which is what our friends at Form Factor do so well. So it needs to happen quickly. You can't spend a week testing a wafer. It needs to be tested quickly, because it's all about speed. In order to do this, this is really where people have trouble grasping it. Doing things in parallel is not something that is easily grasped. It's something that people find difficult to understand. So I want to show you how easy it is. You take an application like this. You divide it into 2 processes. I have an input, I have an output. I need to align an X and Y on the input and on the output. So I have 2 processes. Let's call this process number 1. So you define the process. You say, okay, I want to define a gradient search. Our command is FDG. Let's call this process number 1. And it's going to involve mechanical axes 1 and 2. And this one over here is, we'll call this process 2, and it involves mechanical axes 4 and 5. Okay, so you've done that. They're defined. Now start them. Do them. Do the fast routine start, FRS command, specify process 1 and process 2, and boom, it's done. So it's easy. Everything I've said so far has been about interconnects. But that's not the real future. The real future is new kinds of computing, such as quantum computing, quantum telecommunications. This is not science fiction anymore. We already have 4 customers who are pursuing quantum applications, including some folks at Purdue University. These people are looking at single photon emitters, atomic scale emitters that emit uncorrelated photons, which means photons that have useful characteristics for for quantum applications. So what I did, working with this customer, was develop, this is the result of an aerial scan, where we're scanning many square microns of this diamond material that they use that includes atomic scale defects that fluoresce and perform these, emit these uncorrelated photons. So you can say, with this workstation here, you can say that's an interesting little element right there. And click on it, and the system will automatically lock onto it. This is an atomic scale emitter. The dither radius for the gradient search for this is 10 nanometers. And we can lock onto it so that its properties can be observed over lengthy periods of time. Because one of the benefits of these nitrogen vacancy single photon emitters is that they don't bleach over time. So that needs to be characterized and turned into something manufacturable. So that's an extreme example of what's happening here. We have another quantum customer, has a cascade wafer prober. Okay, when you think about that, why do people probe wafers? They probe wafers when they are going into production, which tells you the quantum is here. It's not science fiction. It's not something our grandkids might see. It's something that's coming right now. So it's exciting times, and our fast multi-channel photonic alignment technology is something that I want to bring to the attention of the field, because I believe it solves a lot of the fundamental problems for the business of photonics. Takes me to my last slide. We have a new tech note on how to use this. It goes into more detail about how to take a typical application and divide it into processes so that it can be easily programmed for parallel execution. Be happy to send that to you. Just give me your business card and I'll make that happen.